So, good morning or good evening for everyone. I'm really happy to be here to talk about this project. In fact, not so just a worker project. First of all, thank you, Hugo, and also Zé Francisco, who is really a friend and came to me to give this talk last year, I think so, or at the beginning of this pandemic. So, as you said, we are going to talk about the homogenization of Schrödinger equations. I should say that the Moscow guy for homogenization is my friend and colleague Jean Silva, who has been working at Universidade Federal do Rio de Janeiro during 10 years, but nowadays is in Federal University of Minas Gerais, UFRJ. And Verne Chaves is our student. He's already finished his thesis with us, and he's been working with us in this subject almost seven years. So he became really a specialist in this field. Okay, so I should say that homogenization is really a nice area in mathematics, really related to material science. In fact, there is a lot of really good, nice open problems. And in particular, we are going to talk about this for Schrödinger equations. We are going to give some brief introduction. Then we are going to talk about the stochastic setting. Then we are going to talk about the main theorem, the homogenization theorem. We are going to pass from some locally compact abelian groups, Sobolev space and local compact abelian groups. We'll try to convince you why this is really important to our contest. And then we are going to give you another application of this theory in what we call stochastic perturbation of the identity. So we are going to give you two examples, really applicable examples of the theory in one problem. And another one is chapter 5, the stochastic perturbation of the identity. So what we are really interested in this principle of stochastic homogenization. In particular, in this project related to Schrödinger equation and Liouville equation, here we just talk about Schrödinger equation. We are interested to study linear Schrödinger equations which somehow describe the dynamics of an electron in a non-crystalline materials. Somehow, most of the time, the Schrödinger equation is posed. The setting is periodic, and then you have this well-known Bloch theorem. So since a material which is crystalline, the mathematical representation of that is a periodic function. This is the usual setting. So we are going beyond this setting of periodic, and so is the way we are talking about non-crystalline materials or non-periodic setting. And to convince you that is really important from the material science point of view, we should say that there exists much more non-crystalline than crystalline materials. So a huge class of non-crystalline materials in particular is if you think that some crystals should say a poor material, but most of the time you have some defect in the crystal. So this defect changes this periodic structure. And how could you represent these non-crystalline materials? A nice way comes from this stochastic deformation, which was a concept introduced by Claude Lebris, Xavier Cabré, and Pierre Lillon. And then you could think that capital phi, if you look to this figure here in the right-hand side, you see that we are mapping somehow a structure that it's a crystalline way in the structure which is no more crystalline. And you could think that it's capital phi omega. Omega is a parameter in the probability space. The name of deformation comes with deformation in the sense of continuum mechanics. Instead of omega, you could think that it should be the time So you are deforming your structure not with the time like a parameter, but with a parameter which is stochastic. Okay? So somehow we are going to consider functions from z to f. This f, you are going to come back with the inverse of phi. This phi will be a diffeomorphism. And here you are considering that f is a stationary function. We are going to give these details in the following. So this is the main idea of this change of structure in the matter from, it could be from periodic, if you think that your function f is periodic, composed with the stochastic deformation, or even more general than that, stationary function composed with a stochastic deformation. So what is the contextualization of our problem? So to begin with, you have been already done, in particular from Aller and Piatininsky in 2005. Let us consider the linear Schrödinger equation. It's no the usual linear Schrödinger equation, because instead of the Laplacian, you have the divergence of some matrix A. So if A is identity, you come to the original Laplacian, more usual Schrödinger equation. And here you see that exists this parameter 1 of epsilon square. So we have two potentials, capital V and capital U. And you could ask me why this parameter could appear here. Well, from some physical points of view, you make some scaling of the parameters in t, time, and x space. And with the distance of the main free path of the electrons, you arrive with two regimes. One of these regimes is called semi-classical limits. And the other regime is called the homogenization process. So here we are in the homogenization process. And this is exactly the equation that Aller Piatininsky has been considering. Epsilon is a fixed parameter at this time from 0 to 1. U epsilon is the only know is a complex value function. The potentials V and U here is assumed periodic, and they are real value functions. And capital A is also a real symmetric matrix, which is bounded and coercive. Okay, so we start with a matrix which is coercive, but at the end of the homogenization process, this matrix could be no more coercive, which means that some of these eigenvalues could be degenerated. So it's the start point. So we are going to pass from this periodic setting to a much more general setting. But what we do like to do? What we do like to do is to make asymptotic analysis on non-crystalline matter. Okay, so there is what we put here, this Liouville equation, because the Liouville equation somehow is a companion equation to the Schrödinger equation. This has been already proved mathematically in precise mathematical terms, but with A is the density. But somehow we have already worked with this Liouville equation with another students, Tainara Andrade, myself, Neves, and Jean Silva, and we were able to give the asymptotic analysis to this Liouville equation. So our project, to put the things in the right hands, our project is to consider at the beginning to somehow to understand how the Schrödinger equation, the Liouville equation comports, give you the asymptotic analysis. So this paper has been already published this year in ARMA for the Liouville equation. Okay, so let's put the things in more precise context. So you are going to say that tau is an ergodic dynamical system. It satisfies the condition that it's the group property. So it means that tau of 0 is identity, and tau of x plus y is given in this way. Very important is the concept that tau preserve the measure. It means that the tau of X, tau of capital R, is a measurable set. The probability measure P in this set is equal to the probability measure in the original set. So this invariance of the measure is very important, because somehow we are going to see the definition of the stationary function, and this is so important this way. And then we are going to choose the property that this dynamic consistence is ergodic. So it means that for every measurable set A with tau of X, A for every X could be in Rn or in Zn. So the probability measure of A should be 1 or 0. So related to this dynamical system, you have the concept of stationary functions. So we are going to consider that a function that from Rn capital omega in R, where omega is your probability space, and we are going to say that this function is stationary if f of x plus y omega is f plus y tau x of omega. Somehow, if we integrate this function with respect to your domain omega, your probability domain omega, if you integrate in both sides, since tau, this measure is invariant with respect to tau, the integral in the right-hand side will be only integral of f of y omega. So it means that the integral in right-hand side in the neighborhood of y with respect to x is giving exactly the same value of fy in omega in the mean value. I should say the expected value. So somehow we are saying that if you take means in respect to probability measure, you look if f represents, for instance, the density of matter, the whole, for instance, it means that when you integrate with respect to omega, the material looks like homogeneous. Okay. So somehow is very important from the physical point of view, and the mathematical point of view is the first, or meaning the best extension from the periodic functions. So we're going to consider most of the time stationary functions in this work. So we introduce the definition of stochastic deformation. This has been already done, or more precisely, was introduced by Alexandre in 1997 in the deterministic setting. Alexander have been working with the homogenization of periodic structures, somehow deformed by this stochastic, not stochastic, but deformation. And then in 2006, this concept was enlarged from Xavier Blanc, Claude Lebris, and Pierre Lilions to this concept, what I'm going to present to you, which are stochastic deformation. And then you have already used this in the Liouville equation, as I said before. So what phi, capital phi will be is a function from Rn omega to Rn, and this function is a homeomorphism for each omega fix. Okay, so you could go from one side to come to another with phi minus 1. So the essential infimum of the determinant or Jacobian of the capital phi should have a bound from below. So this should be bigger than or equal nu, which is strictly positive. Somehow it's saying that you are not deforming, you could not concentrate. Okay. So somehow, like in continuum mechanics, your Jacobian could not change sign. Okay, when you pass from one point to another point, and somehow your gradient should be less than equal m, which means that you could not deform so much. So you have some control, which the first derivative of phi, somehow you could not pick up a point, 2 points which are really close from the beginning. It could be so much spread with the deformation of this stochastic deformation. And the more important point is not phi itself, but the gradient of phi behave like a stationary function. So it's very important that the gradient, because the gradients are going to give you the idea of the deformation. So the idea of deformation, when you take expectation values, the material looks like homogeneous. This is really nice idea to consider material science that looks like a perturbation of the identity or perturbation of the perfect material using this idea of stochastic deformation. Claude has been extending these ideas somehow to this type of material science, but most of the time considering just elliptic equations. So this is an example of stochastic deformation. I mean that it's not set, it's not empty set, okay? Somehow you are going to perturb the identity y with some function which is periodic. You have some control of this gradient somehow. So there are some examples of stochastic deformation that really accomplish some idea of materials. Well, related to this stochastic setting is the concept of mean value. It's not just related to stochastic, I mean, it's periodic functions. Deterministic periodic functions has the idea of mean value. So if a function is in L1 log of Rn, we are going to say that this process a mean value if the sequence for f x of epsilon converges in duality of L infinity for each compact support functions to some constant, which we call it mf. Equivalently, you have this limit in this sense. This is somehow is a standard in this concept of homogenization, the idea of mean value. And related to the mean value, you have the compactness theorem, what we are going to use to get compactness. Somehow the Birkhoff-Ergodic theorem are going to tell you, that the realization of some function f in L infinite bonded, measure bonding Rn with values in L1 of omega, for each omega tilde fix, so somehow we call this realization, the realization of a function with this property, which is a function which is stationary, then this function has a mean value, and moreover, this mean value is given by this integral in the right-hand side. So somehow Birkhoff gives you the idea that the stationary function has the mean value for almost all realizations. Related to the Birkhoff theorem, you have this Birkhoff theorem accomplished by the stochastic deformation. So somehow there are two works with Blanc-Lebris in Lyons, and he was able to prove that a stationary function composed with the stochastic deformation processes a mean value with almost each omega fixed, and this mean value is given by this integral. Okay, so somehow we are in good hands to say that we are working with stationary functions or even periodic functions composed with the stochastic deformation. Things goes well. This was published in 2006. Okay, related to linear Schrödinger equations, even for the beginning in deterministic setting, you are going to use the concept of two-scale convergence. So for one that is not so well familiar with the two-scale convergence somehow is in between from weak convergence and strong convergence. So it's the nice idea to work with linear homogenization, linear partial differential equation, what we would like to make the homogenization. This was introduced by Knut in 1989 and well developed by Haller a posteriori. But here, as you're going to see, this is a two-scale convergence in the stochastic sense. So we are going to say that a sequence in L2 here for almost all omega fix converge to some limit which depend this omega tilde fix in this set of epsilon here is 0, 1 in a potential, it's the torus, 0, 1 a potential n, or the dimension of the domain, Rn here, and in omega your set of probability sets So the two-scale covariance are going to tell you that for some test function, convenient test function in this class, which are described here, okay, which means that S is a countable set of smooth stationary functions, né? This limit exists and is given by this expression, okay? So two-scale convergence appears exactly in the homogenization theory. Related to this two-scale convergence, you have this compactness theorem, which tells you that if your sequence in L2 is uniformly bounded in L2 respect to epsilon, then you could extract a subsequence, denoted here by epsilon prime, and there exists a function U tilde such that this U epsilon converges to scale to this U tilde. Okay? So we are going to use this in here in the linear Schrödinger equation, stochastic linear Schrödinger equation, this idea of to pass to the limits with this compactness theorem. More than that, it's very important, these two sets, capital A cursive and H cursive, which are functions f, which are stationary, and has this regularity, which one is L2 log in Rn with values in L2 de omega. So this is a Hilbert space and could consider inner product in this way. In the same way, we are going to consider this looks like the H1, usual H1, but you see that since omega does not have any structure, we are going not allowed to think that you have some Sobolev structure related to this space. At the end, we are going to tell you how could you put some structure or how could you consider Sobolev space in this omega if you think that omega is a group. In fact, a locally compact abelian group. But here at this time, at this point, omega does not have any structure. So you just have the notion of Sobolev space with respect to the y variable. The Rn variable. So if you have estimate, so let's talk about this theorem. So if you have uniform estimates with respect to epsilon, to your sequence U epsilon and epsilon gradient of epsilon, this epsilon appears here because of the 1 of epsilon square in front of your potential. So it means that you are not going to obtain, you do not have uniform estimates in H1, but just this U epsilon gradient of epsilon. Then for almost every omega tilde in omega, there exists a subsequence, and this subsequence converges to scale to some limit point which depends on omega tilde, U omega tilde, and more than that, epsilon gradient of U epsilon prime converges to scale to this the matrix, Jacobian matrix of phi applied to the gradient of in respect to the is y is related to the oscillatory variable, the rapid oscillation variable. So we are going to in fact choose exactly this theorem. Okay, so let's now let us present what are exactly the equation we are considering. So you have this Schrödinger linear equation. So again, you have this 1 of epsilon square in front of the potential V. You have your potential U, your matrix, which is measured and bounded and coercive, symmetric, composed with your stochastic. All of the coefficients are composed with the stochastic. At this point, we are going to say that just the initial data is given by U0 epsilon, but in fact, since this equation, is linear, we are going to consider somehow prepare initial data, which means in some sense that your initial data is parallel to some eigenfunction. We are going to see briefly. So we are going to consider that your tau is a ergodic dimensional system, the blah, 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 your potential boundary real stationary functions. Okay. So, as usual, in the concept of Schrödinger equation, we are going to multiply the equation by U bar. You're going to take the imaginary parts. So, which means that you are going to get your L2 energy estimate in L2 of your function. This means that your U epsilon is given by the energy of U epsilon is equal to the initial time. And more than that, if you multiply by UT bar, you're going to get this estimate for epsilon gradient of epsilon, which is just what you could obtain with this equation with epsilon square, 1 of epsilon square multiplied the potential V. Okay, these somehow are standard estimates. So now you talk about what you call a spectral cell equation. This comes back to the book of Jacques Lilion, or the homogenization book or material science book of Jacques Lilion. The standard, not the standard, but the basement book of homogenization. And what you usually do when you are trying to work with homogenization problems, you make expansion, asymptotic expansion. You consider that your solution of your function U epsilon of your equation is given by some series, and then you introduce this series in your equation 1 and collect terms which are powers of epsilon. So epsilon a power 0, just 1, epsilon power 1, epsilon power 2. When you do that, you have been discussed with Francois Morat. This does give you exactly the homogenization process, because this asymptotic expansion is just formal, but gives you the idea what the term you have to consider. So somehow you should pass from this asymptotic expansion. So we are going to consider, when you do that and collect terms, you arrive to this stationary equation, which in fact is eigenvalue problem. If you think is this an operator, and you call this Lphi of theta, for each theta, this is operated on F, given by this expression. And in fact, you have to find the eigenvalue psi related to the eigenvalue lambda, which satisfies this problem. So to resolve this eigenvalue problem, you could think with the variational formulation. Then to obtain lambda and capital Psi, you have to resolve this variational formulation. So if you remember well, the course on the usual course in analysis related to the Schrödinger equations, you see that you need somehow the compactness, the Rayleigh-Kondrakov theorem that assure you the compactness of H1 in the usual deterministic setting, okay? Gives you the compactness of H1 in L2 in order to resolve this eigenvalue problem with the associated variational formulation, okay? So somehow we need, in this context of stationary context, this eigenvalue, this Rayleigh-Kondrakov theorem to resolve this eigenvalue problem. But somehow one could think, well, if you fix omega, this is really just usual standard eigenvalue problem, the deterministic eigenvalue problem, and I could apply the Rayleigh-Kondrakov usual theorem. But it could be not the possible. This could not be the way to do that, because somehow your eigenvalue lambda, you depend on this omega fixed to resolve this in the deterministic way. But this lambda could not depend on omega, and we are going to see so soon, because the homogenized matrix star are given by the agent of this lambda. So at this point, so this is why we are talking about this cursive H, compactly embedding in AL cursive. No, it's not true in general. And at this point, we assume that you have resolved your eigenvalue problem, and there exists some point theta star and also lambda of theta star, such that this lambda is a simple eigenvalue, this theta star is a critical point, which means that the gradient of lambda is 0 at this point theta star. Okay? And then to resolve your homogenization problem, we are going to consider the prepared initial data. So it means that your initial data is given somehow in the direction of some eigenfunction of your precise eigenvalue problem. Why is it very important to consider that? Because since your problem, your equation, Schrödinger equation is linear, you could apply the superposition of effects, and then somehow, and since this lambda, it's lambda, in fact, PC, it's a basis in the Hilbert space, could be considered as a basic space, or at least you could truncate for some of the points, some of the elements of this base, and you could consider that your initial data is the sum of some directions or some eigenvalues PC. For simplicity, we are going to consider just one, because if you know how to work with one, since your problem is linear, you could work at least with a finite sum. Okay? So, and then there exists this V0 with a same infinite function with compact support. At this point, somehow we are following the same ideas like in the book of Jacques Lyons and the others, né? And also the idea given by Allaire in Piatninsky. So at exactly this point, we are following, but in a much more general context than periodical context. Okay? So again, it's not so difficult if you are going to consider that your initial data is uniform bond in L2, and you have this uniform bond epsilon gradient also in L2, you are going to give to obtain that your sequence U epsilon is uniform bond in L2, and epsilon gradient of U epsilon, your solution of the linearized stochastic Schrödinger equation, you get the nice estimates to apply the compactness theorem. So then we arrive at the homogenization theorem, or the main theorem of this talk. So consider that theta star satisfies the conditions before, and your initial data is a prepared initial data. Then there exists a function U epsilon, which is the solution of the Schrödinger equation for each epsilon fixed, okay? And then you consider this function V epsilon from this U epsilon written in this form. Clear, this U epsilon, this V epsilon should satisfy for t equals 0, the V0 before. And what this theorem tells us, if you write V epsilon from this U epsilon, which are solutions to the Schrödinger equation, this function, this sequence V epsilon, two scale converge to the limit, which is some function V of t and x, which are solution this Schrödinger equation where A star is constant, is a constant matrix, times your eigenfunction PC, which you have considered before for the initial data. And more than that, this looks like a corrector. You see that I did not tell you, but it's exactly the strong two-scale convergence. You are saying that your function P epsilon obtained in this way, two-scale converge to this function. So somehow you are giving you the idea of how is the convergence of your corrector. Unfortunately, you are not going to, this goes to 0, but it should be very interesting, just not consider the limit, but if you could have the rate of convergence of this term with respect to epsilon. But somehow you could say that at least this corrector goes to 0 as epsilon goes to 0. So this
Well,
function
by the way,
v.
do you have any guess of what would be
Sorry.
great? Do you have any guess?
Not at all. Not at all, Hugo. It is a good point, and you are going to work with in particular for more general Schrödinger equation. It's very important in particular if you are thinking more on other terms. But no, I do not. We do not have this guess at this point. Thank you. This is very important. This is really very important. So somehow I should say that there are some people, experts in homogenization, which are really interested in this rate of convergence for the correct term, because it's very important when you're trying to apply some numerical scheme, numerical analysis. But if you think that this problem is already so complicated, we are not talking about a linear elliptic equation, which is already well known. Everything is really well known. So this, we should say that this took a long time for us, for me, Jean, and Verne, because it's terra incognita. We do not know nothing. We do not know even, it was so many ambitious to give this like a thesis, okay? So somehow, but it's a really, really good question. And then your function V satisfies this limit process, this homogenized Schrödinger equation with, I could say, could put here this constant matrix, which is no more cohesive. Okay, so it means that you're going to get the uniqueness of this problem just because of the L2 estimate. And more than that, this homogenized matrix is given by the agent of lambda, your eigenvalue with respect to theta. And since this matrix is constant, this lambda could not depend in omega, as I told you before. This is not a process. I mean, it could not depend on omega. And the potential is given by this expression, is somehow is almost given by the two-scale convergence in the paper of Allaire Piatninsky. Just to give you the sketch of you have almost a little bit more than 15 minutes, but let's give you just a sketch of for the step one is a priori estimate in two-scale convergence. So we're going to get the a priori estimate for V epsilon, for the estimates for U epsilon, as I showed before, by the compactness theorem for the two-scale convergence for omega tilde fix, this V epsilon converge to this function. We put here a V star because at this point V star depends also on T and X and Y, the oscillatory function, the oscillatory variable, and omega. But in fact, we could show, using the idea of factorization idea, that in fact this V star is in fact a V which depends just in T and X, multiplied by, but let's see here, multiplied by your eigenfunction, which in fact depends on omega. So I will do that as usual in the paper from, not usual, but comes from the paper of Allaire. You multiply the function, the equation one is your Schrödinger equation, stochastic Schrödinger equation, by a convenient X function, and you pass to the limit, and we are able to arrive to this equation for your V. And since these coefficients does not depend on omega, by the uniqueness of the solution of the Schrödinger equation, you obtain that your V omega tilde does not depend on omega no more. Okay, at least for almost all omega tilde in omega, capital omega. And it means that your V epsilon tilde converges somehow to your function V times your eigenfunction. In fact, it's your eigenfunction composed with your stochastic deformation. Okay. So now, to finish at least this outline of this proof, we are going to show this a correct type result, which are the strong two-scale convergence. Somehow you open this square, I mean, by a product, scalar product. So you're going to arrive this VS square 2 times the product, and this one 2v square. When in fact this v epsilon square is exactly the u epsilon square, and from energy estimate, this is exactly the u0 square, your initial data, and then we arrive to this point, and pass to the limit. When you pass to the limit, as epsilon goes to 0, the first term is exactly v0 times this term. You see that it's no more to take the real part because this is just real, because you see before you have this times this v bar. So you each arrive this quadratic term. Any more than that, I did not show you, but you have this energy estimate that it means that these guys are also equal. So it means that this term is equal to this term minus 2 of these terms. So you arrive at the limit of epsilon of your strong two-scale convergence is equal to 0. So you arrive at this property of your corrector goes to 0. Okay, let's talk about this theory of local compact abelian groups. Let me see the time. Okay, you have already 15 minutes, exact 15 minutes. So the main motivation to study subalapse space on groups, besides being an elegant and modern mathematical theory, is related to the eigenvalue problem. You see, find the number of theta, which could not depend on omega, and the eigenfunction in this space, okay, satisfying that problem 2, which is the eigenvalue problem as I showed you before. Indeed, we may use a compactness argument. That is, the space HV is compactly embedded in L2, in L of phi, this coercive L of phi, in order to solve the associate variational formulation, as I told you before. One more time. Although omega cannot be fixed, remember that the matrix A star is the agent of lambda. Hence, we are going to establish an equivalence between this space and some subalapse space on groups, and then consider a related Rayleigh-Kondrakov theorem in this general space. So somehow now, to resolve this eigenvalue problem, we are going to give some structure on the probability space omega. As usual, let G be a locally compact abelian group, and we may assume without laws of generality that associated topology is Hausdorff. We are going to denote the G hat, the dual group of G, and is given by the set of the characters of G. Okay? Moreover, we may enjoy this G hat, the dual group of G, with a topology with respect to which this set is itself a locally compact abelian group. In fact, even if G is not locally compact abelian group, G hat is. Just to fix the notation, we are going to see that mu and nu are the unique Haar measures with respect to G and G hat with respect to a multiplicative constant. Somehow we could think that when we pass from Rn to this structure of local compact groups and use the Haar measure, you are saying that invariance from translations are very important. Now you have already, you are forming a nice really group in homogenization here in Rio de Janeiro and Minas, or I should say in Brazil. And this property of translations are very important in homogenization. So you are getting the structure of invariance from translations exactly when you have this in Rn. Any more than that, we are going to use the Fourier transform, we use this exactly in this way. So given a complex value function f in L1 of G mu, the function f hat in the dual space of G, defined by this way, is called the Fourier transform of f on G. A quick book to understand this is a book from Folland, in general harmonic analysis on groups. So we consider capital P, the set of little p from G hat in this same line, which P are continuous and invariant pseudometrics on G hat. So since this P are continuous, we are allowed to take any x, y for this function P in this pseudometric G, and then you define gamma x exactly from the distance from x to the identity element, which is the identity element in G hat, which is exactly like the function 1. Somehow this gamma x is mimicking the idea of the norm. So somehow you're going to see briefly, when you're going to define the Sobolev space, there is a norm of 1 plus model of Kc, some potential, and this gamma x are going to give you exactly this notion. So somehow we are going to define this norm, like from a metric, from the distance to the origin. I mean, how could one say that this P is not empty? There is a nice theorem from Birkhoff in Calcutta that ensures you that P is not empty. Okay? So we are going to define what we call it in this project energy Sobolev space. Okay? So given an S, non-negative real number, and gamma of x given by 4, like before, for some P in capital P, the energy Sobolev space as HS gamma of G is the set of functions f in L2 such that this expression is true. So some ones that have been working with Sobolev space in Rn recognize so well this expression. More than that, give a function in this space, the norm of this function in given by this expression. I should say that we are going to work just with S goes 1 in this work. An example to recognize so soon, if you take G of Rd with the action of the sum, which is known to be a local compact abelian group, and you consider the dual group of Rd given by these guys, so A0 of x is just to take y equals 0, so A0 of x is 1, and we are adopting this notation. So your semi-metric is given by this way, where this is the usual Euclidean norm, and then you consider your gamma of x in this way, and so it appears 2 pi here, but somehow since Rd dual is almost the Rd, you could be considered G, the Sobolev space SS gamma of G coincide the usual Sobolev space in Rd. And we have another examples in our paper, which is already almost finished. We give the torus and the infinite torus, although 2 more examples, but we're not going to talk here about this. So since we know that the measure of G is finite, only if G is finite, and since we are going to interpret G like your set omega, which is a probability set, I mean, you are going to consider probability measure, we'd like to consider just G, which are with mu is finite. Therefore, from now on, we are going to consider that G is compact group. And hence, mu, after some up to normalization, we could consider that Ju mu is a probability space. Related to this probability space, now G mu, we have to consider to link this with dynamic consistence before. I mean, the idea of dynamic consistence before. So somehow we are going to define a dynamic system in this way, convenient in this way, where phi from Rn to G is a given continuous homomorphism. It's very important to characterize what are the conditions, the properties of this mapping phi. Somehow this phi looks like the compactification, Bohr compactification. But I mean, you have to realize that this phi it's not allowed to be anything. I mean, you have this nice theorem that gives you some conditional phi. The dynamical system given by H is ergodic. Since you have to work with dynamical system with ergodic, you have to have some condition on phi that ensure that this tau is ergodic. So this is true if and only if the image of phi from in Rn is dense in G. So you are able to characterize exactly what are the conditions. So since this is a necessary and sufficient condition, that this tau is ergodic. Now, for the dynamical system established before, the main issue is how to relate this H1 gamma, which you have been defended before, with this space H cursive phi, what you have been working with our problem of the eigenvalue problem to obtain the psi and lambda. Okay? Just here to fix the ideas, we are going to consider that phi is the identity. So you denote this when phi is identity, denoted by just H. So which are the functions, stationary functions with this regularity? And the inner product, this is a Hilbert space, you consider this inner product. So the main question at this point is, what is relation? What is the relation from this H phi cursive with the H1 is given exactly in this theorem. So a function f in this class belongs to this class if and only if f in the point 0 is a H1 gamma of G. And moreover, you have this equality of norms. Okay, it remains to get the Rilke-Kondrakov theorem. So you consider there a map from L2, the dual of G to L2 of G, defined in this way. This is exactly what appears in the integrand of the definition of the Fourier transform. Oh, sorry, the Sobolev space. So give me this operator, we could make an equivalence theorem, which tells you which thing. The Sobolev space H1 of gamma is compact embedded in L2 if and only if the operator T is compact. So somehow you have the Rilke-Kondrakov theorem if this T is compact. Anyway, so you are going to characterize exactly what are the conditions to have this Rilke-Kondrakov theorem from the property of T. And these are going to give you exactly these conditions from this dual of G, and then from this gamma, which is related to somehow to the norm in the correct space. I mean, we are able to give the first theorem, which is a necessary condition, which means that if the operator T is compact, then your dual space of G is at most enumerable sets. So this is a necessary condition for G hat in order to be compact. And then you have a sufficient condition with respect to gamma. Let us consider this following property. For any D positive, the set of the characters have this property. The gamma in this character is less than D. This set is a finite set. Then you have the characterization of the Rilke-Kondrakov theorem that tells you if gamma satisfies this condition C, then the operator T is compact. So you have characterized which are the conditions to have the compactness from H cursive to R cursive, or at least from H1 gamma in L2 of G. This theorem, Rilke-Kondrakov theorem, has already been proved before. But the idea of this characterization, which are really important to our understanding, which are the sets, which are the contexts omega that you have this compactness to get the eigenvalue eigenfunction solution, are important at this point. Okay, so an application of this context. So I was going to. Why do you have this huge gun? Now you have general homogenization theorem. Now you tell us that with some properties of omega, capital omega, like a compact abelian group, we could get the solution of the eigenvalue problem. But give me some results. Why this is not so? This is not empty. So this is exactly a very important example. What we call the quasi-periodic coefficients. So this is exactly an important example that you have already solved the eigenvalue problem and could apply our general homogenization theorem. Okay, so I will skip these details. We hope so soon the paper is going to appear, and then you pass to another direction. We are not have so much time to tell you, but why now we are going to consider a perturbation, stochastic perturbation of identity. I mean, we had considered the compact groups to resolve the eigenvalue problem. So I'm going to show you another way to resolve this eigenvalue problem, perturbing somehow the identity. Okay? So now your stochastic deformation depends in some small parameter eta. Okay? So this is the first term, eta 0 is the identity, and then you consider the first term eta or capital Z, where capital Z is also a stochastic deformation. So this perturbation was considered before by the group of Pierre-Lilions, and he was really interested in the homogenization process related to the application for numerical analysis. But here, our idea is to show you that if you compose periodic functions with this type of stochastic deformation, it means that when you are in the first term, or the zero-order term, you are in the periodic setting. But the periodic setting could be resolved exactly by the quasi-periodic coefficients. What I'd like to say exactly. You already know in the periodic setting the eigenvalue and the eigenfunction solution of your eigenvalue problem. And since you are perturbing this periodic setting, you could get the eigenvalue and eigenfunction, which are perturbations of the periodic setting. And you could apply, in fact, you have already done this, you could apply the Cato theory of perturbation, Cato's perturbation theory, but you have made all the counts in the details. But I think that my time is already past 3 minutes, and we are almost at the end. So just tell you this story, and then you have here the reference that you have been considered for this problem. So Piatninsky and Allaire, the main one. This is our work, the Liouville equations. Here are the two papers from Xavier Blanc, Côte-Levy, Pierre-Lilions, where they introduced this idea of stochastic deformations. And other papers, this one, Gorja and Reis, is the paper which appears for the first time, the proof of the Rik-Kondrakov theorem in the group setting. So this is well-known book from Zhikov and Kozlov, and I should say thank you so much, and I hope I could see the face now. Hugo,